Hello everyone. So in this example, we're going to look at another way that we can calculate the Gibbs energy of reaction. So we're asked to calculate the standard Gibbs energy of reaction at 298 Kelvin for a given reaction. So we're looking at mercury sulfate reacting with oxygen, so it's actually an oxidation reaction, where it's going to form mercury, liquid mercury and sulfur dioxide. And we're given some thermodynamic information, which is the Gibbs energy of formation. Right, so then we're given this table here. Where's my pointer? So we're given the Gibbs energy of formation for the reactants and the products. And then we're asked also what is the reaction product or reactant favored at equilibrium. Right, so this is an example where you will hopefully recognize that you can calculate the standard Gibbs energy of reaction using the formation Gibbs energies in a way that's analogous to calculating the reaction enthalpy from the formation enthalpies, right? So if we recall that we can calculate the reaction, the standard Gibbs energy of reaction through the sum of the formation Gibbs energy of the products minus the sum of the formation energies of the reactants. All right, so we use the same way. So let's sum our products and then that for our reactants. So if we write out what the mechanics look like, we will see that, well, our products are of course mercury liquid multiplied by that of the mercury liquid formation Gibbs energy, and of course sulfur dioxide, and each of them only have 1 mole, so the stoichiometric coefficient of that is 1 mole. All right, and I write out the units for that, so it's 1 mole of mercury liquid per mole reaction that forms, 1 mole, etc. And that's then subtracted from that, we have the reactants. So you do the same for that. So there's 1 mole of mercury sulfide that reacts per mole reaction multiplied by the Gibbs energy of formation of mercury sulfide, and then 1 mole of oxygen gas per reaction that reacts multiplied by the Gibbs energy of formation of oxygen gas. All right, so where do we get these values, these Gibbs energy of formation? Well, they're given in the table. All right, importantly, Gibbs energy of formation works exactly the same as what enthalpy of formation is. Works that for elements and for things like gases and diatomic molecules in their standard states, meaning standard states. So for example, whatever you would see or encounter an element or gas or whatever at 298 Kelvin. However you would encounter that species, that means the Gibbs energy of formation for that would be 0. So for hydrogen, oxygen, fluorine gas, chlorine gas, bromine liquid, iodine solid, you would use the value of 0, right? Mercury is a liquid at 298 kelvins. In other words, it has a value of 0. And then sulfur dioxide and mercury sulfide is a solid, who is a compound, right? So it has, these things have Gibbs energy of formation, right? Which we always can use as indications of how stable these compounds are at these conditions, right? But anyway, we're going to plug them into here. So that's our next step. We put them into the equation, and then, you know, where the zeros go, we can then ignore, and then of course we put them at the appropriate places, right? So remember where the negatives, what are you subtracting from what to help you calculate. And eventually I got here to a point where I got a rounded value of minus 250 kilojoule per mole reaction, right? So remember the units that you're working with for formation Gibbs energy are kilojoule per mole, and the unit of a stoichiometric coefficient is mole per mole reaction. So how that will cancel, mole will cancel with per mole, and then you're left with kilojoule per mole reaction, and that gives you the unit of the standard Gibbs energy of reaction, which is kilojoule per mole reaction. All right, so that gives us the first thing that we had to calculate. Calculate the standard Gibbs energy of reaction. All right, So then we asked, is the reaction product or reactant favored at equilibrium? Right, so now we must look at the sign of the Gibbs energy of reaction. So what does the sign of the Gibbs energy of reaction tell us? Well, firstly, we see it's negative, right? So that means when the standard Gibbs energy of reaction is negative, it means we form a product-favored equilibrium. Product-favored equilibrium. All right, and that is specifically at 298.15 Kelvin, right? But under standard conditions, so we will form a product-favored equilibrium because the standard Gibbs energy can tell us whether or not the equilibrium will be product-favored, reactant-favored, or if we are just at a perfect equilibrium. All right, so that is what we get from that information. Cool. So that's the mechanics of it. I mean, a lot of writing, but at the end of the day, it's just straightforward calculations. Right, thank you for watching, and I'll see you in the next video.